Let's do it.
Ready to go?
No, we still got to wait at least a minute.
Cool.
Let's see, who RSVP'd that we need to wait for? Oh, Chris Latner RSVP'd. We should wait for him.
That's it for today. It was fun hanging out.
What's really sad is I haven't done any iOS development in so long. I forgot his name. I had to look it up. It hurt me. Let's see, it's 6:31. I guess we can begin. So you ready, Amir?
I am ready.
Okay, cool. Hey, everyone, welcome to the July meeting of the North Dallas Developers Group. Today, or tonight, I guess we should say, we have Amir. He's going to be talking to us about the modern landscape of programming languages. This is going to be fun. We're glad you're all here. We're hoping, by the way, and this is a big announcement, we're hoping that this will be our last virtual meeting for quite some time. Starting next month, we will start meeting at Improving's offices. That's up on Legacy and just east of the tollway. If you came to our meetings at InThrive, you basically go past InThrive about a block and you get to Improving. So very close to the old location. So that's going to be really fantastic. I think we'll get the free pizza. That's going to be awesome, and it'll be great to actually be able to meet in person again. So that's going to be next month. All right. So Amir, I don't know. Should I introduce you, Amir, or are you going to introduce yourself? Amir has spoken for us many times. Friend of the group for many, many years, and so we're glad you're here. And why don't you go ahead and kick it off, and we'll watch. Oh, before you do that, sorry, my fault. If anyone has questions, please put it in Slack. We'll be watching there, or in the Zoom chat. And so we'll wait till Amir is at takes a breath and is at a stopping point, and we'll ask those questions. So anyway, now cool. For real, go ahead.
All right. So we are going to talk about the technology behind the abstract title is the technology behind next generation programming languages. I think that's it's a really interesting topic. I guess just a little bit of background with regards to myself. I started digging into this around 2016. Excuse me. And it's been the most challenging work I've ever done in my entire development career. It's kind of weird. It's still I still feel like I've barely hit I'm at the tip of the iceberg. And what I'm hoping to do is give you a kind of a 10,000 foot view, give you a lay of the land on what interesting things exist out there, and maybe just help inform you with regards to what all has happened, I guess in the last decade. So before we start, there's a book that I read, and it's actually a pretty good book. It's called Algorithms to Live By. The computer science of human decisions because of course I want to eventually become a computer. And one of the interesting aspects, or one of the other interesting lessons that was elaborated on in there is this concept of an ACK. And just in the Zoom call, we have the HTTP requests that are going back and forth, the TCP network negotiations that are happening. ACKs are being sent, and an ACK is essentially saying, hey, I got the message, send me the next one. Hey, I got the message, send me the next one. And with Zoom meetings, the challenge is that ACKs are less prevalent. It's hard for me to see people and actually see the responses, nods, or confusion in their faces, which will probably be quite a bit during this presentation. And so I created a silly little app that we have right here. And what I would like y'all to do, it's really important, is to go to this website. Akmoji, AKMOGI.herokuapp.com. And when you go there, you will be presented with a control panel of sorts. And if you click one of the buttons, what I'm hoping to see, if the app works, we should see someone's thing show up on the screen. So each one of y'all gets randomly assigned a discrete position on the screen. So it's anonymous, but I know I can at least see the feedback that's coming. So now we have an ACK system. So it's just like we're in person again, sort of, except you're limited to these emotions. All right, it looks like it's working. That's great. So I'll be looking at the screen, and as I'm talking, if I see emptiness, that means that I should probably leave. But hopefully, this will keep you all entertained at least a little bit. Okay. Who here has anyone? So we can use the ACK system now. It's going to be cool. Who here came to my the last presentation I gave, the 7 lessons for after 7 years of game dev? So at least 2 people, 3 got 3 people. Who did not show up? Who wasn't able to make that presentation? Oh, sad faces. That's so sad. So this will be a little bit of a rehash of something that I talked about in the presentation, and it's about kind of how this compiler took over the world. All right. So in 2005, this guy named Chris Latner finished his PhD in computer science. Smart guy. And around that time, he was hired by Apple. Okay. Now, Chris Latner has a computer science PhD, and he observed something about the landscape of I guess, compilers. And for that reason, Apple hired him. And in 2007, Apple released the iPhone. Okay. iPhone took over the world. It sold very well. And a year later, in 2008, Chris Latner was, I'll just say CL, was published in a scientific periodical based out of Italy. I forgot the explicit name of the article itself, or the periodical, but that's when this new compiler tool chain was announced. It's called LLVM, stands for low level virtual machine. And what Chris Latner observed was that the C and C++ compilers of that time around 2008 were stagnant. We have 2 main compilers. We've got GCC and we've got VS Visual Studio or MS VS, the Microsoft's compiler, Microsoft's C++ compiler.
Visual C++?
Visual C++, thank you. MSVS, yeah, MSVS or MSVC, VC, there it is. MSVC, there we go. And these were the two compilers that existed. So Chris Lattner introduced this compiler toolchain called LLVM, and he created a new compiler called Clang. And on the announcement of Clang, he was able to take C and C++ code and compile it just like GCC and Microsoft Visual C++. And the execution of the code was 20% faster. The compilation speed was at least twice as fast, and then the execution of the code itself was 20% faster. And this was a big deal, and it was a big deal. It was a strategic move by Apple itself, which we're going to see as this story progresses. So in 2010, Rust comes into the scene, and Rust uses Clang as its default compiler. Cool. In 2011, Objective-C 2.0 comes out. And with the 2.0, they introduced auto-ref counting, which is an updated way of doing garbage collection. And TensorFlow entered the scene. It also used Clang. All right. With the introduction of the Arc compiler, Laurent Sanzanetti, he worked at Apple. He had an implementation of a Ruby, a programming language that was also implemented using Clang. It's called RubyMotion. And so he left Apple and created a startup to create this additional compiler. 2013, Dart. Guess what Dart uses? Clang. Now it gets interesting. So C# devs out there? We have some C# devs. Got some thumbs up coming up. Cool. All right. I was obviously definitely invested in the .NET industry, still am. No sad faces. C#'s great. It's a great language. C# .NET Core was announced. And in 2014, I didn't understand the reason for .NET Core to exist. So now I understand, and hopefully, by the end of this presentation, we'll all have a better understanding of this. All right, 2015 comes around, and this is where things get a little bit interesting. The Apple Watch releases. And what's important about the Apple Watch is that it uses a chipset that is not x86 or ARM. These are fairly standard chipsets that exist, x86 being our laptops. ARM devices would be our mobile devices. But the Apple Watch was using something that was neither x86 or ARM. It was a custom chipset. And it was a chipset built by Apple. Now, the interesting thing, and this is where LLVM and Clang starts showing its benefits. Because they used this compiler, they were able to implement the binary compilation to allow for the targeting of the Apple Watch. So just keep that in mind. We're going to go into details about what that means later on. But 2015 was a very interesting move for Apple. It kind of hinted at what was going to happen next. Another thing happened in 2015 was the Objective-C 4.0 ended up happening. You've got additional enhancements with regards to language features, speed, obviously with the targeting of the Apple Watch, just general updates to the language itself. 2016, V8 becomes targeted by Clang. So V8 is what's used to power Chrome, the Chrome browser. So effectively in 2016, Chrome is being built using Clang. So by 2016, we've got Microsoft starting to invest in this new tech. We've got, of course, Apple, who's leading this compiler approach, and now Google's come into play. 2017, we're almost there. Chris Lattner leaves Apple and goes to Tesla. So what does that mean? It means Tesla's using Clang, right? I forgot to mention in 2014, we also had Swift coming out, new programming language by Apple. And another thing that came out in 2014 is TensorFlow. Guess what TensorFlow uses? Clang. It's getting scary. We've got TensorFlow, which is a Google tech, Dart, Google, CSharp, Microsoft, Apple, V8 is Chrome, Tesla's in the game now. The Nintendo Switch comes out. Its compilation target, Clang. You also have Emscripten. Emscripten is effectively a means to take C code, C and C++, and convert it into a JavaScript-like assembly language. And we'll cover things like what about Blazor and whatnot, and how that is part of this little relationship here. But now you've got the Web Consortium actually being invested around the same time. All right.
Question real quick. Clang,
yes.
Is it a compiler or a compilation target?
That's a good question. So Clang is a compiler. It's a C, C++, and Objective-C compiler. So we've got Clang, GCC, and then MSVC. So these are the three big players in the field as far as 2008 where it was concerned. And slowly, a lot of these companies, especially the new tech that they're building, is starting to use this instead of these two compilers. Okay, makes sense. All right, 2018. Yeah. What happens in 2018? Well, Android API 26 comes out. And in Android API 26, there's a native development toolkit, which is called the NDK. And so if you want really fast C APIs, you use the NDK. And in the NDK, there are build tools. There's a build tools directory. And there's something that changed in the build tools directory. The build tools directory no longer referenced GCC build targets. It now references Clang. So API 26, Google moved away from GCC, and for their mobile devices also started to use Clang. At that same time, 64-bit ARM started to become a thing. So they were starting to transition, the devices were starting to transition to ARM 64. And at that point, that conversion happened. Now, something interesting happens. Oracle comes into play. Like, where the hell did Oracle come from? Out of nowhere, 2018. Oracle has a big investment in the JVM, and they introduced a runtime or virtual machine called Graal. And if you think these names are crazy, they get crazier. Don't worry, you're going to be laughing towards the end of this. So they introduced Graal. Now Oracle's in the play. 2019, Visual Studio 2019 releases. And inside of the build tools and build packages that are available, you can use Clang as a compiler target for C and C++. So not only can you, yes, Microsoft Visual Studio is still an option, but this shows up inside of Visual Studio 2019. That's a big deal. to have that just like quietly put in there as a project aspect. 2020, aside from all the terrible things that occurred, C# 5.0 releases. So C# 5.0, Microsoft removed the .NET Core branding. There's no core branding anymore, and the unified runtime is called C# 5. And C# 5 targets Clang. It's compiled with
mean .NET 5, not C# 5?
.NET 5, yes. .NET 5. So by 2020, and then Sony PlayStation came out in 2014. Yes, that also uses Clang. I forgot to mention that. So
We'll see.
PS4 came out here. So by 2020, you've got Tesla, Nintendo, Sony, Microsoft, Apple, Google, Oracle, all using Clang. And then the big coup de grace, I guess, it was in 2021 when the M1 processor came out. And at that point, what Apple did was because they positioned the compiler to such that all programs were compiled with it, there was less of a worry of compatibility, program compatibility being broken for a chip that no compiler actually targets. So they were able to create this M1 chip, and because everyone effectively is using Clang at this point, programs worked on the M1, right? So this was quite this is effectively the tipping point of where Apple was going with this strategy. And it all originally started with the, of course, hiring of Chris Lentner at the beginning of 2005. And then in 2014 or 2015, the creation of their first really, really tiny chip, their exploratory chip for the Apple Watch. And then from there, the M1 shows up. So Clang has taken over the world. And this opportunity to ask questions, but next thing we're gonna do is like, what the hell is this thing? Why is this the thing? Why over I guess a 15-year period did it just knock out the big contenders with GCC and MSVC? What happened? So I want to explain that. I mean, I'll explain that next, but I wanted to give a moment to potentially opportunity to ask questions about what this timeline that occurred. Any questions? Any thumbs down for questions?
No questions at the moment in the chat, but if anybody has any questions, please ask them.
Okay. Thumbs up if you'd like me to move on. Everyone still awake? Hopefully. Cool. Nice. Look at that. Woo. All right. So what the heck is LLVM? What is this thing? How did it take over the world? Why is everyone using it? What caused this this transition? So LLVM is a group of tools. Okay, it's a group of tools that handle the optimization of an intermediate representation. Okay, so first and foremost, LLVM is an intermediate representation of a language that is not C, C++, or any other language you've used. Okay, real quick, let me show you what that looks like. Okay, I have a C file here, and it's a real simple function. It's just an add function. I add 2 numbers, and then I return number 1 plus number 2. Okay. We'll go into a lot of the cool things that C has added later on, but hopefully this kind of frames what LLVM looks like. The interesting thing with Clang is Clang has a special flag. Come on, there you go. And this special flag, the switch that you see here is called emit LLVM. So Clang has the capability of creating the entire binary for you, but it also has the capability of just creating, of just exporting the intermediate representation without doing the full compilation itself. Okay. So I'm going to do that. I'm going to do the export. And if you notice, there's a new file that was created. It's called, and it has got the LL extension on there. Okay. Let's see what add.ll looks like. This is LLVM. Okay. This is your intermediate representation for that function that we created in C. And the interesting thing about this representation and why it was so important and so valuable is that this representation has no dependency on the language that it came from. It is completely isolated. Okay. And the beauty of that is that if you have, so Clang is able to emit LLVM. Well, the LLVM compiler toolchain has something called LLC, which is the LLVM compiler. And what LLC can do is compile intermediate representation. So regardless of what your front-end language, effectively they're called front-end languages now, regardless of what your front-end language is, as soon as it's got the ability to emit LLVM or intermediate representation, LLC is able to convert that into a compiled binary. Okay. And the thing is that GCC didn't have this capability. They had a form of an intermediate representation, but they still had a strong dependency on the source code itself to determine different kinds of optimizations that can be performed on it. And the value, that's the big value of this format, is it's almost human readable. You can almost read it. See, this is our add function. It's this is a statically typed intermediate representation. We've got two integers that are passed in. These percent values, %0 and %1, are essentially in place integer variable names, and these integers are set to specific values 3 and 4. We store those values as 32-bit pointers inside of the 0 and 1 register. We load those values, and then there's an LLVM function called add, and then we return 7. Now this is an unoptimized debugs representation of LLVM. What I'm going to do now, if I do, I'm going to do the same emit LLVM, but I'm going to set the optimization to 03. Why is it called 03? I think it's for compatibility with GCC. But when I do the optimization level for 03, if we look at the file now, we can see how this code has been optimized. So all of those register shifts that occurred get resolved down to these specific instruction sets. And this is where the power of LLVM comes in. Is the intermediate representation, once it's created, can then go through these optimization passes that are part of the LLVM toolchain that do different types of optimizations. So an example of an optimization would be this is called a strength reduction. So if you have 8 divided by 2 as a C function, you can do the division of 2 integers, but technically the faster optimization would be to do a bit shift that way, right? I don't know the exact syntax, right? But if you do a bit shift, this is actually faster than doing the actual division itself. It's called a strength reduction. There's quite a few of these optimizations that are applied via LLC. And the beauty of that is that you don't have to worry about this. If you emit LLVM and this intermediate representation, the rest of the compiler toolchain is able to optimize what you provided and create a faster binary. So the intermediate representation is an important part of it. And here's the crazy thing now. C++, basically all the languages I mentioned are transpilers now. And I mean, I remember back in the day when CoffeeScript was a thing, and people would say, "Oh, CoffeeScript just transpiles to JavaScript." But we're in this world now where anything that targets LLVM is effectively a transpiler to this intermediate representation. So, is that a bad thing? In this case, no. It's actually really great because we've got this infrastructure, this LLVM infrastructure that operates on IR, is able to do the compilation, right? It's able to do optimization. And there's also something called LLDB, which stands for low-level debugger. So now we have a unified debugger. If you're creating a language, you don't have to worry about creating a debugger anymore. If you target LLVM, you will be LLDB compliant. And you'll be able to step through code and it will just work. Okay? So you get that. And then the other thing is that you don't have to worry about your targets, your chipset architectures. So the way it works, you have your front-end language. You've got your intermediate representation, and then you've got your target. They're called backend compilers. So this would be your x86, your ARM 64. M1 would be here. Okay. And these backend compilers. So you've got your front end compiler. You have your intermediate representation. You've got your backend compiler, and these compilers spit out your ones and zeros, right, for your specific platforms. So if you're a language designer, you create this. The intermediate representation is created, and you emit the immediate representation. And when some large company, because again the world runs on Clang now, creates a new chip, your language automatically supports it. You don't have to do the work to create the binary output for that new chip type. And there are chips coming out all the time, right? You've got ARM64, you have ARM32, x86, ARM64, M1. GPUs are part of the market now. So Vulkan is a GPU by NVIDIA, and because their backend compiler uses Clang, any front end that can compile to the intermediate representation can be targeted directly and have a program run on this GPU. It'll just work, right? Ortega, the Ortega chip, I think that's the Nintendo Switch, right? You've got your Qualcomm, which is what Apple used to run on before they created their A star chips. But this backend compiler was also available there, right? And because of the success of the iPhone, if you wanted to have hardware that was part of iDevices, Apple required you to implement a backend compiler using LLVM. If Intel came to Apple and said, "Hey, we want to continue having Intel chips inside of your Mac, but you have to use GCC," Apple will say, "We'll just go elsewhere." And it's a weird position where Intel has to say, okay, hold on, we will implement the backend compiler for you. Sorry about that. And everyone kind of fell in line. And because of that, the ubiquity and the power of this compiler kind of converged, allowing, and then everyone said, well, I mean, this thing already implements all the stuff we need, and all the hardware manufacturers are already creating the backend compilers, and we should just use it. Right. So that's what LVM is. So any questions about kind of like this, the intermediate representation, this how this architecturally works out to be everyone's benefit. Fairly clear on this? I'm sorry.
Request. Compare and contrast this with, we're used to in the .NET world of
Okay.
or in the Java world of Java bytecode.
Perfect. That's a good question. So how is this different than IL? Right? Why is IR? What is so innovative and compelling about IR? And Chris Latner, he's just one of them guys who knows his stuff. IR in the intermediate representation is a virtual machine. So programming languages effectively take source code and convert it into 3 operation opcodes, such as this, right? Add, return, store, a lot of the things that you were seeing inside of the LLVM implementation. But they're usually really simple machine codes that are then leveraged to do the optimization and then the compilation. There's a caveat though. IL is a stack-based VM. And stack-based VMs, your program counter and your machine codes, if you have a stack that you manage your function execution. So when you execute a function and you have to do a jump, whatever program state is pushed onto the stack, it jumps to the new location, it processes the program state on this side, and then it pops back out to this top level location. In layman's terms, that's kind of what happens with the stack-based VM. The caveat though is that IR is a register-based VM. So there's no shuffling of this stack up and forth, back and forth. And what you effectively get is a virtualization of an infinite set of registers. So you don't have to worry about an array being a stack pointer to a bunch of array values. The array can just live in a register. And the other interesting thing about these registers is that they're immutable. So if I set a register value, we had the percent sign 1. If I set that register value to 6, I can't set this register again. I have to set another register to, let's say, 6 plus 2, taking percent 1 as the value. And this is important because what this gives you is the ability to apply an optimization scheme called static single assignment. And what the SSA optimization scheme does is you can do dead code elimination because all the registers are immutable. You can do dead code elimination based on the usages. So if you know, this will essentially, like if I in C, if I did, int I equals 0, and then I do I plus equal 1, the LLVM would be, your percent 1 equals 0, and then percent 1 prime is equal to 1. So there's a I guess like a trajectory, a scale, like an audit, a trail back to the original implementation. So if later on in the code, if you find that nothing ever leverages percent 1, then you can remove this line and then inline it. So any additions of %1, everything, if everything uses %1 prime, then this value of 1 prime can then be substituted in there. And so the combination of being register-based and a stack-based VM allowed for this optimization to occur. And this is what like blew away the compilers that exist today, the GCC and MSVC compilers, because they were all stack-based. And so the challenge comes is that IL, the intermediate language, is a stack-based virtual machine. So I don't know how far they got inside of .NET Core, but a part of this .NET Core rewrite that had to occur for C# was converting the virtual machine from a stack-based VM to register-based. Now you can do stack-based stuff and kind of translate it over to register-based, and you still get a few benefits. But to get real power of LLVM, your virtual machine has to be completely. It's like an upheaval of your virtual machine and move it over. I mean, that's why it took them 6 years to do it, right? And so that was the kind of like the differentiator, the edge, or like that's how it worked, right? That was the gotcha aspect of why this ended up being so powerful. And the interesting thing is that with these register-based VMs, or the register-based virtual machine, when ARM64 came out, now we're in chipsets that are able to leverage these many registers. Your M1 processor, I don't know, I'm not sure how many registers it has, but I'm sure it's more than your x64 processors. So you have programs that actually run faster because the virtualization of the registers within an LLVM can now be mapped to real chips, real points on the chip itself. So your x86 processes, if it's using a register-based VM, actually run faster on M1. So it's that initial architectural like insight that allowed for this like kind of shift to occur. Does it make sense?
It does. Thank you.
Any questions?
I don't see any.
Okay. Is anyone awake? Is anyone going to Acme? Come on, we need some Akmojis. All right, we got a few people awake. Cool. Are you finding this interesting so far? Like, I know we've gotten some like we're gonna get in some a little more technical stuff, but this context is fun to know. Is it gonna help you on your day to day? Hopefully, just having this insight will help you kind of evaluate and see languages from a different lens, and maybe we'll have a powwow or thing at the end and kind of do a little retro. Okay, so here's the thing. What is LLVM written in? It's written in C++. So wait. So Clang is written, Clang in the LLVM toolchain. Clang is a C++ compiler, but it needs C and C++ because it's written in that. Does anyone see a problem here? What the heck? What do we do here? Well, that's where GCC and MSVC comes in. So the compilation of Clang is bootstrapped through the usage of GCC or Microsoft Visual C. So you can use either one of these compilers to create, and this is kind of crazy, right? You can use either one of these compilers to compile LLC, which is what we used, and Clang. Okay. Now these versions are inefficient versions because they don't have the optimizations of Clang. They use unoptimized versions of GCC and MSVC, but Clang is able to emit LLVM. So instead of using GCC, you use GCC to create LLC and Clang, but then you use the emit LLVM switch on Clang source code to emit .ll files. And then you take those LL files and use the unoptimized LLC to create an optimized version of Clang. And now that you have an optimized version of Clang, you go back and create the optimized versions of LLVM toolchains like LLC. And then the next version of Clang uses the previous version to compile itself. Now this begs the question, how the hell did GCC get there? If you need GCC to compile Clang, okay, that helps and then you use Clang to create an inefficient version of Clang to emit LLVM to create your LL files, which can then be sent to LLC, which creates the fastest version of Clang, which is then sent back to LLVM to create its fast version. Now you have this performant version of Clang. Well, what about GCC? How do we get that? Well, this is completely ripped from a Stack Overflow history, but the way that works is there is a assembler language called hex 0, which can be written by a person, and it's 375 bytes. So a human has to write this assembler code for a specific chipset processor. It's the only processor that would work. I think it was either 386 or it was x86. So using hex, now you've got this higher level language called hex 0. Hex 0 can be used to create hex 1. Hex 1 can be used to create a little bit higher level language called hex 2. And the hex 2 assembler is just enough to create a mini language, a mini implementation of C called cc_x86. Now, cc_x86 is just enough to create something called MES, MES, which is a Lisp, which is a scheme interpreter. It's Lisp. Now, this can then be used to create your slightly better version of C called MESCC. MESCC can then be used to create TCC, and TCC can then be used to create GCC. And then when GCC is created, the next version of GCC uses GCC. So this is the dependency stack here.
We have a question. How is Grail VM similar?
So the question is Graal VM similar? We'll ask in a second. Okay. Well, so with regards to the virtual machines, actually, yeah, we're at the end of how this Clang stuff happens. So we can get into actually talking about the virtual machines themselves. And Graal VM effectively is the Java virtual machine used to optimize, to do an additional suite of optimization passes on the .ll file. So what Graal does is it takes these .ll files and says, we're going to use the JVM as a backend compiler. So they're essentially using Java and the JVM as an intermediary compiler that spits out LL. Now, the interesting thing about this Graal compiler and why it's called Graal VM and it's not explicitly Java is that it's a virtual machine. And the virtual machine has leverages Clang. There's parts of the virtual machine that are written in C, but the virtual machine allows for, I guess, perfect compatibility for dynamic programming languages. So you take your Ruby source code, you compile it via Clang, you send it through Graal, you get a new .ll file, and now this Ruby source code, this Ruby compilation, and the Ruby interpreter itself is actually faster than compiling from Clang, from just Clang. And what the Graal VM does, it uses effectively aggressive caching and memoization. So when you invoke a function in your application, it takes some time to warm up, but you get to the point where the trajectories and the passes of your program are effectively hard-coded and cached to the point where this becomes blinding fast. And it is. So this implementation of Ruby is called Truffle Ruby. And it is, I think, anywhere from 5x to 20 times faster than C Ruby. And the ability, the reason they were able to do that is because of the lever is using the Java virtual machine, and they're using the JVM as a backend compiler, which is also insane. And there's his name is Chris Seaton. He got his PhD, and he was the one that spearheaded the initial implementation, which is Truffle Ruby. And then with Truffle Ruby, they're also targeting Clojure, and then effectively any dynamic language. They might do JavaScript. It's all up for grabs at that point. But that's kind of how Oracle created their value prop, was saying that we can take, everyone's concentrating on these statically typed languages like C#, Swift, and everything. But the interesting thing is that the JVM and its JVM bytecode is actually surprisingly dynamic. It's not a static VM, even though Java itself is a statically typed language, Java, Scala, Kotlin. But the JVM bytecode and its intermediate representation is actually quite dynamic. And so it was a good fit for dynamic languages. And then so things like Truffle Ruby and Clojure, JavaScript become targets for an additional LLVM optimization pass. But that's kind of how Graal fits into this. And it's, yeah, when it was announced, I was like, this is not, how is this even possible? Obviously, I don't have a PhD, but you install Truffle Ruby and you do the performance, you're like, this is 20 times faster than regular Ruby, and I don't know why. I still don't understand it, to be honest. Again, for me, it's at least for our implementation in our company, our LLVM specialist. I've just got the tip of the iceberg. Our LLVM specialist is Alex. Is actually Alex Denisov, and he's a Clang LLVM engineer for GitHub. So he's currently employed at GitHub. But this is our Clang guy. I'm more on the runtime side, which is actually what we'll be getting into next. So that's Graal. What do y'all think? Any thoughts, questions, comments? Is this overwhelming? Is this good? Is it a good pace? Any confusion where we're at right now?
This is great. Thank you.
All right, cool. So this begs the question, what the hell is a language? What is a language? And we use this term, I think back in the day, saying that you use C# was okay to say. But today you can't say that. You can't say that I use C#. And the reason is because there's all these permutations of C# and Ruby and JavaScript and everything else that we'll look at. So we can't say what is a language anymore. I guess we kind of want to say what is a language, what language implementation do you use? And when you say language implementation, it's comprised of three things. You've got your language spec. You've got your core libraries. And then you've got your runtime. So these three things together are what create your language implementation. Okay. An example would be if someone asked me, what do you code in, what language do you, what do you use, or what's your stack? I can't say C#. I'd have to say .NET 5.0. And actually .NET 5.0 is the runtime. So I'm using the C# language spec, the C# 9 language spec, or C# 8 language spec, provided via .NET 5.0, which is not the same thing as your C# language spec on Mono, right? Which is not the same thing as the horrible, crappy, trash implementation of C#. I can't even. They're not even 2-spec relative to Unity. It's kind of C#, but it really isn't. But people say it's C#. It's kind of C#, but additionally, the runtime is Unity, which is an offset of the Mono runtime. And then when it comes to core lib, well, your core lib depends on, are you using standard lib, standard C libs? Are you using Windows.h? Like those become your core libs themselves. But yeah, that's where the water really gets muddy, right? If you're a JavaScript dev, you can't say you're a JavaScript dev. Well, what JavaScript? Is it V8? Are you a front-end dev? Is it what's it called? Node? That's another implementation, runtime implementation. So you might be saying, okay, I run ES6 on Node, which is different than saying ES6 on V8. They have different core libraries. They have different implementations. So to expand on this example, let's say I'm going to write some C# code here. So I'm going to create a var person, or let's say I have a person object, an if statement. If person equal line, throw an exception. Think about all the permutations. If it's null, does it throw an exception? No. Well, is it possible for this line to throw an exception? Thumbs up or thumbs down? Call your shot. Oh, someone's like spamming thumbs up. The answer is it depends on the runtime. If we're talking about .NET 5, yes, this line can throw an exception. Because if this thing is a struct and this thing is a class, you will get an exception. Now, the equal operator implementation is specific to the runtime. The language spec says that this syntax is valid, but it's up to the runtime to decide what equality means in a specific language. In the context of .NET 5, this if you try to compare equality of a person of something that's a class and of something that's a struct, they'll throw an exception. Okay. Here's another caveat. You've got a string class in .NET or in .NET 5. var name, let's say, is equal to some name. Is this a value type or a reference type? Who thinks it's a value type? Thumbs up for if you think it's a value type. Okay. Thumbs up if you think it's a reference type. All right, we've got some thumbs up here. Okay, so if I pass this into a function, if I have a void function, void, foobar, whatever, we'll call it B, and you take in the name, can I mutate it here and have it affected? If it's a reference type, can I mutate it and have it affected outside of this function? What do you think? Is it will it, if you pass in a thing and then alter the name, will it be changed outside the function? No, it is not. So string is a reference type that has no mutable mutable methods. So the plus operator on string actually returns a new string. And the equal operator is assignment of a pointer, which assigns it to a new pointer, so you don't affect the original pointer that was out there. So it's a reference type which with no means of mutating it. Okay. So these things like the equality, the actual representation of your string. These are runtime considerations, and they're independent of the language spec itself. The language spec might provide some information about what equality should look like, but it's up to the runtime to decide exactly what that should be. Let me give one more example. So with Node.js, the interesting thing about this runtime is that yes, it uses ECMAScript, as its language spec, right? But its runtime has one of the differentiators of the Node.js runtime is its non-blocking I/O and its event loop, right? So everything in Node is non-blocking, and it's got this concept of an event loop at the top level. Your front-end browser doesn't have this concept. You apply properties and it's all sequential and blocking. But Node.js uses something called, remember when I said that there's going to be like crazy names? It uses something called libuv for its event loop. And libuv is a C library, and it stands for Unicorn Velociraptor. That is the name of the C library that handles the event loop for Node.js. And if you're using Node.js, you are using something, you're depending on a runtime that depends on something called Unicorn Velociraptor. Congratulations. But it's an aspect of the runtime itself. Language is JavaScript or ECMAScript, but the runtime provides it that asynchronicity. Okay. And then core libs are the final piece. When you do file IO, how does that happen? Is that even possible with the runtime that you're using, right? If it's V8, you can't use the dirstat, right, which is a standard library. You can't do it until mscripton, which allows you to have access to file storage or isolated storage. So your language spec, your spec plus runtime plus core lib. This is what creates the thing that you're working with. Okay. And that's just kind of how it is now. It's confusing. It's really, really annoying. Especially with .NET Core and .NET 4.7 being a thing. You can't say, I work with .NET. It's like, well, which .NET, which runtime, and that informs a lot of things that go downstream, right? Ruby, JRuby would be another thing, obviously. Ruby is your C implementation. JRuby is the Ruby language spec implemented on the JVM, right? So these are different runtimes. Of course, Dragon Ruby. I'll go into details as far as why the hell did we make another runtime, but Dragon Ruby is at this level, right? So the final aspect of this, and this goes back to everything using LLVM. If everything is using LLVM, and everything goes to LL, and everything, and if LL is all static compilation, and if everything goes to the same optimization passes, how can you say if a dynamic language is faster or slower than a statically typed language? How can you say that? Well, the answer is you can't. You kind of can right now, but over time, these performance heuristics will converge to to kind of a baseline where if you're using Clang, the language is going to be fast. It's going to be as fast as the optimization passes allow it to be. Okay. There's one caveat though, and this is another aspect of Clang that makes it so powerful. Is there something in Clang, or LLVM, sorry, and they're called LLVM intrinsics. So LLVM intrinsics are here. What we see here, this add function, this add NSW is an LLVM intrinsic, right? They have intrinsics for loops. They have different opcodes for a lot of different things that you can do. Okay. So your differentiator in your language and in your compiler is how well you use these LLVM intrinsics. Here's an example. Everyone familiar with matrix multiplication? Right? You've got, matrices with some values, and then you do a multiply with another matrices of some values, and then you get a resulting matrices, right?
Are you trying to draw something? Because we can't see it. And when you're at a good stopping place, we have a comment and 2 questions, by the way.
Right, so LLVM intrinsics and matrix multices, and yes, we'll be at a stopping point after this explanation of LLVM intrinsics. Okay, so this is matrix multiplication. Now, the fastest way, what used to be the fastest way to do matrix multiplication is if C# has does C# have a matrix class? It might. I think it might, maybe. Let's say C# has a matrix class. If the implementation of that matrix class for like a 3x3 matrix, that's, I guess that would be n squared or n cubed, big O of n, I think it's n squared. If you do this in C# and you use for each loops in C#, that gets converted to IL, which is stack based. And then that goes down to Clang and then all the way down. Now, you could do it in C instead of C++, or instead of C# and use for loops. And because the Clang compiler in C uses a register-based VM, your output will be faster. So your matrix multiplication in C will be faster, which isn't surprising. That's pretty common. The gotcha though is that there's an LLVM intrinsic that exists, and it's called an LLVM matrix intrinsic, and it understands how to do multiplication. And so the challenge with LLVM is that it can only optimize nested for loops so much. There's no way to communicate that this combination of nested for loops is a matrix multiplication. So the virtual machine exposed an intrinsic that said, we're going to give you an intrinsic that does the multiplication for you. And then the backend compiler, the developers of the backend compilers will be responsible of converting that LLVM intrinsic to something that runs efficiently on their chipset. Right? So when we go back to this idea of can a dynamic language be faster than a static language? Well, it depends on how well it uses the intrinsics. In fact, if a C implementation doesn't use the LLVM intrinsics, and the built-ins that are like a physics library a physics C library that was created and didn't use these built-in intrinsics, it's possible that a dynamic language would be faster than C because it might be leveraging the intrinsic directly. So this is kind of like where the world is coming to, is that it's the means of using your LLVM representation, but also having your core libs leverage the intrinsics that exist on the platform itself. And then you're relying on the backend developers and the hardware manufacturers to convert those intrinsic values into something that runs extremely fast on their systems. So an example for the M1, if you give it a matrix multiplication, the M1 processor may decide to say, this could run on one of our GPUs, even though it's not GPU related, because matrix multiplications are so fast on GPUs, we're going to do it there and then return the value. And that's something that the backend compiler, backend LLVM compilers can do for you on your behalf. Right. So that's kind of where things are converging to from this like compilation runtime core library standpoint. It's how well you use these LLVM values. Questions, comments?
All right, so there's a comment that I believe goes all the way back to the Unity discussion.
Okay.
Somebody says, was old mono version, but it's .NET Core now supposedly. Can you?
No, it isn't.
Not?
No, it's not. They do have a new Unity implementation called the Burst compiler. And the thing with the Burst compiler is that this actually uses LLVM. So when Clang became a thing, and then when their targets had to be iOS and Android, Unity was a variant of Mono. They forked it, and Mono emits IL. So how are we going to get this IL to work on iOS and Android? We have a limited amount of time. People are asking, when are we going to be able to make mobile games? And they're in this position where they're like, we don't have the time to re-implement, a language implementation. We're not a near $1 trillion company like Microsoft. We can't do this. And so what happened was that there's a project that exists called IL to CPP. And what they do is this IL gets sent through this transpiler, which creates CPP files, and then those CPP files go through Clang to create, and then go through the specific ARM64 stuff, and then you get your binary. So this is how they did things for a very long time. The Burst compiler is something that's been introduced in the past year or two, and the Burst compiler actually, does not use it's their register-based implementation of C#. Here's the gotcha though. Their core libs. So it's a language spec, which I still don't think they're compatible with 8.0. I still don't. They're still not compatible with that. It's kind of infuriating there. So they're not compatible with that. It's a C#. It's a C#. It's not the C# 8.0 that is the de facto C#, but it's a C#. And now it uses actual like LLVM intermediate representation. The problem though is that their core libs are incompatible with Mono. So where you used to do a list of int, you can't do that anymore. It has to be a native array of int and some variant of that. Native array of int does not have an IEnumerable, so you can't use link statements on it. And so this divergence occurs with the creation of the Burst compiler. So yes, you get all the benefits of speed with your Burst compiler, but if you've got a game that's already built using the existing Unity runtime, are you going to recode it? Are you going to recode it to leverage the Burst compiler? It's the question. And so that's kind of the transition that they're going through right now.
Mm-hmm.
Yeah.
Next question is, how would you classify TypeScript?
How do you classify TypeScript? Okay. So the answer is I haven't looked at TypeScript source code, but what you would do is you would clone the TypeScript repo, right? GitHub repo, and you would just do a recursive search for the word LLVM. So if you see any C libraries or any inclusions of this, you know that it's doing some kind of IR. It's at some point emitting some kind of intermediate representation. And if it's not doing this, then it might be converting to JavaScript, which is then being converted to which is, yeah, definitely using Clang and IR. So I suspect that's what's happening. And if you look at .NET Core, if you clone .NET Core and you search for the word LLVM, there's a specific class that everyone uses. It's called IR Builder. This is you use this class to actually create that assembly language that is shown here, and we're gonna see what that looks like. But you don't handwrite this; you use the facilities of LLVM to create this. But to know what a language explicitly uses, that's what you're gonna have to look at. So .NET no longer uses IL. You'd have to check .NET 5.0, but I haven't confirmed it. I haven't verified if 5.0 actually did the transition. But if you clone the source code for .NET 5.0, you will know very quickly whether it uses the VC Microsoft Visual Studio compiler or not, based on the usages of these constructs here. I'm expecting that .NET 5.0, at least from the marketing material that I've seen online, is it's a cross-platform implementation of .NET, which means that it's not using MSVC. It's probably using Clang. Yep.
But in theory, you could go to IL, and the IL could then be compiled down to LLVM.
So that's the thing with the core compiler, is that to get the full power of LLVM, you can't go to IL because this is a stack-based representation, right? You have to parse this C# code and emit the intermediate representation, and we'll actually take a look at that now. I think this is a good segue into that. So yes, you can take this technique, and in fact, .NET initially did this. They codenamed it Lilac. And it was basically IL to CPP, but from a Microsoft variant. So the initial workings of .NET Core, when they were just trying to get some semblance of using C# on other platforms with Clang, they explored Lilac to create IL to generate IR. So they didn't create CPP files. They just said that we know these opcodes exist. We just need to find the right intrinsics inside of LLVM and just map them over. It's not 100% efficient. It's still a stack-based VM, but at least we're getting all the benefits. So that was codenamed Lilac, and I think it's still online.
Xenobrain says that Unity Burst actually does compile from IL.
That's unfortunate.
And just checked that .NET Core does compile to IL first as well.
Okay, so what's happening is that they're still leveraging. They're not getting the full power of LLVM at that point, right? Because they still have a stack-based virtual machine, unless IL has been transitioned to a register-based. That could be a possibility too. But we'll show some code there. Any other questions and comments?
Last one, and then we can move on, unless none of them comes up. Question: all these also apply to interpreters?
So yeah, the question is, do all these apply to interpreters? Interpreter is a weird word again, because LLVM also has a JIT, so a just-in-time compiler. So something that could be interpreted can be JITted, and then it's no longer interpreted. It's interpreted at that point in time, but then you got your call site caching, and then that execution path is now compiled LLVM code. So interpreted means maybe interpreted for a short period of time, could be a long period of time. It's just a matter of how the LLVM JIT is incorporated into the evaluation of that interpreted code. So I think looking at this will shed some light. So here is the compiler written in C that leverages Clang, And what you see here is a program that prints hello world. Okay. So we're going to kind of go through this. You create your top level God object context. This is using their straight C API, which is, again, just the tip of the iceberg. Their C++ API is really what you want to use to actually create a real thing. But the first thing, LLVM and the LLVM intermediate representation has a concept of a module. So a module is effectively a namespace. Okay. Here's the IR builder. So this is going to be IR builder inside of C++. And then I need to create a couple of LLVM types. I need to create an integer pointer of type 8, which is a char. I need a char pointer, and then I need an integer value. That's your int32. Okay. Now, because C uses LLVM, the functions that it compiles and creates through its standard lib are available to you. So printf is available to you at the LLVM level because that language was compiled, the C language was compiled using LLVM. So printf is available to you. So for your language, printf takes in its argument type. It returns an integer value, and it takes in a char pointer, which is your string, right? So you can use these. You can use any language's standard lib and leverage it inside of your own language. Okay, and this is exactly what's happening here. So LLVM add function. I'm saying I want access to printf. I'm going to create another module called main. Entry point is your main block. So LLVM has this concept of your main execution block, and then if you have conditionals, they're kind of like go-to statements. They look like go-to statements, and we're going to see this when this is compiled out. So from there, I create a final return value, which is I create the final function argument, which is a combination of the output value and the input string, and then its effective pointer value. You invoke the function, and then you store the value, and then this context is then, and that module is then LLVM print file is what does the compilation. So we're going to see this. We're going to see hello world show up on the screen. There it is. And let's look at what the compilation output looks like. So program.ll is right here. And all that code that you saw generates this intermediate representation right here. And let's look at the build script, so you can kind of see, like, look, ma, no, nothing up my sleeve. Main.cc is a compiler. Remember, it's not a program. It is a thing that created a program called Hello World. And when you invoke it, it creates the intermediate representation. You use LLC to compile this, and then that creates a .s file, which is a bytecode file that Clang understands, and you can use that to create your program. This is insanity. It's insanity, but it works. And the reason it works is because once this is generated, the source of how this was done is just not necessary anymore. Magic is greater than sanity, and this is one of the reasons I wanted to do this presentation, is that it feels magical, but it's effectively you're provided machinery that allows you to take the semantics of a language and map it to a virtual machine instead of having to invent one yourself. So the IL is an invented virtual machine. The JVM is an invented virtual machine. These are all virtual machines that are created. So instead of saying I need an add function or a move function or a jump, you look at what's available as far as opcodes and intrinsics inside of LLVM and invoke those instead.
So if we decide we want to create our own language, right? So LLVM becomes that can be our runtime, but we still won't have any standard libs. And we'll have to essentially create something that will compile to LLVM bytecode.
Yes. And LLVM is not your runtime. It is your opcodes, because you can use the opcodes in certain ways to create your own interesting implementation of your runtime. Right? If you want a C# implementation where equality doesn't throw an exception between structs and classes, you will need to you would need to compose the LLVM intrinsics in such a way that allow for that to occur.
Well, that's obviously what I'm going to do tonight. So you still need you still need language compiler and virtual machines still leveraging LLVM.
Yep.
And you still need your standard libraries.
So that is actually a great segue into Dragon Ruby and what we did there. But here is the language spec for LLVM right here. This is all the things it can do. So if we look at our module structure, so this is your module structure. Let's say you want to do a jump or like a conditional, right? I think it's called cond. Widen condition, experimental intrinsic. Yeah, so here's your cond. So basically you have a BR, I think it's BR. There's different semantics for it, but you give it your true value and your false value and then the labels, and then here's your labels, right? So this is your true path and your false path. So here's your go-to statements effectively. I was talking about the matrix intrinsics. Here they are. So instead of doing a for loop, your matrix library should expose a class that explicitly emits this intermediate representation here. And if you do that, you've created a matrix multiplication API that would be faster than something implemented directly in C that uses for loops. And the thing is, like, a lot of these contributions as far as like matrix multiplication and vector math are related to TensorFlow. Machine learning has a lot to do with a lot of these intrinsics. So the existence of TensorFlow has allowed for some of these mathematical functions to exist. Same thing with vectors. Your vector type, standard lib vectors, might not be a thing anymore. You can just use the vector intrinsics. You don't need to create an array list implementation. And if you do, it will be slower than this. Right? But the spec is massive, right? This is a very large, very, very large specification. So it kind of makes sense to take the approach of, okay, we have this IL, we just need to find the right, and IL representation, I think is 3 operand also. It's pretty close to that. We just need to find the correct LLVM opcodes to run, and then just translate between those two, and then don't touch it. The problem with that is that you don't get all the benefits of doing that. And that's going to take us into how do you create a real LLVM language? Like, how is Swift created? How is Rust? How is Objective-C created? How are those things created? Before I move on, any questions on this stuff?
There are no questions in the queue.
Okay. It's insanity, but this is an innovation. I mean, like, it's taken over the world. This structure and the ability to have these data structures and the complexity that you see here allows the next phase of the LLVM infrastructure to work, which is all the optimization pieces and the backend compilers, right? So you pay for it here, but you gain it back by having effectively any chipset architecture target that LLVM supports, plus all the speed that any other LLVM language would have. It's really cool. All right. So we've talked about language implementations. We've talked about kind of how LLVM works. We've talked about like LLVM intrinsics and how the line gets muddy between, you know, what is a dynamic language versus a static language, what is interpreted when the JIT is involved, when you can compile on the fly. These things are really starting to converge. So your biggest differentiator, so what become your biggest differentiators of a language? One, how do we build one? And then two, what are the differentiators if you decide to build a language? Okay. So high level, let's cover how do you build a language? Okay. You've got a spec. You've got a spec of sorts. And that spec is read by a developer, hopefully. And the developer creates a file. And this file is sent to better C# compiler.exe. What does this thing do? Okay. First thing, so there's general steps to doing compilation. You've got your tokenization. Let's make sure our emojis are there. All right. You got your tokenization, which takes each one of the items, each one of the language constructs, and creates little tokens of their location. You've got your parsing mechanism. And your parsing mechanism takes those tokens and converts them into semantic, uses context to determine if that parentheses is in the right place or not. So you tokenize a string to, so like this is definitely a parentheses, or this is a keyword, or this is a, you know, function start or function end, but then your parser is what determines whether that is successful or not. LLVM does not help you with this. Okay. So what are the solutions? Well, you're gonna love this. You've heard of Yak. You've heard of Antler. So Yak is yet another compiler. It allows you to declare a language specification and using something called a context-free grammar. Think of regex, but different. And then that will generate C code that will create your tokenizer and parser and let you know if whatever was created whatever the file is, if it's valid or not. There's Yak is called yet another compiler. The next version of Yak is called Bison. I'm embarrassed for an industry at this point. I'm seriously like, you get into this world and you're just like, we are just trolls all the way down. And from here you can kind of figure out why Antler is called Antler. I swear, everything's terrible. Kill me, right? Kill me now. But there's another way you can do it, and it's called a recursive descent parser. And a recursive descent parser is you basically say, I'm going to pretend this stuff doesn't exist. I don't want anything to do with these mammals. I'm just going to parse the code manually, like God intended. And this is actually what C# does. So C#, the Clang implementation of C++ and C, they all use recursive descent parsers to create their languages, to create their language. Ruby uses Bison. I don't know about everything else, but I know that C# uses a recursive descent parser. I know that Clang and C++ use recursive descent parsers. The thing with them is that they're easy to reason about. You don't have to learn this yet another thing. It's a bit more work, but it could end up resulting in compiler information that's better and more informative. Okay. So now that you have your parse tree, then you start looking at emitting IR based on that parse tree. So the conventional approach is that once you have that parse tree, you go to something called code generation. It's called code gen. And this is where you decide, okay, what are your opcodes going to be for your virtual machine? What are they going to look like? And then you create your, your add opcode for your virtual machine and your stack-based virtual machine and program counter and everything. And then that gets converted to bytecode in some wonderful magical way. But I said magical. I don't understand. You have your opcodes, and those opcodes are virtualized inside of a program counter and event loop, usually written in C. Now that's different for LLVM, and let me show you what that looks like in LLVM. So if you look at there's a LLVM, and Bison is not BSON. Bison is Bison. Oh, this is great. This is the world we live in. Okay, so parser and AST, you decide what you want to use: recursive descent, Bison, Yak, Antler, what have you. And then when you have those AST nodes that are created, your abstract syntax tree, you then use LLVM's IR builder. And you recursively go through each point in the tree and you say, compile the left side, compile the right side. So in this case, situation, if I see a plus sign for a specific token in my AST, I want to call builder.create float add, and give it the left side and give it the right side. And then you give it a function name or module name that is accessible to the rest of your runtime. And there's a lot of intrinsics. There's a lot of different things that IR Builder provides you. In this case, this language provides you plus and minus. And things like GCC parallelization and a runtime definition. So LLVM has GCC intrinsics and exception intrinsics called unwind. So those are all part of LLVM. Your parallelization depends on what threading library you use. Do you use POSIX threads? Do you use was it OpenMP? I think that's a threading library created by IBM in C. That is up to you on what you want to use there, right? But some things are conventional enough to where it's been pushed down to the virtual machine itself. In the case of in the case of garbage collection and exception handling, it's part of the runtime. These are things that you don't have to implement; you just have to learn it and say, okay, if I see this open curly brace, that means start a function, or if I see a rescue or a catch block, that means that I need to do an emit and unwind intrinsic or opcode, which is part of the intermediate representation. And I'll handle those aspects for you. And then once you have that, you do your like print code gen wherever that happens inside of this madness. It's somewhere. I can't find it, but we did it over here, right? Module to file. The moment you have that, you've got a program, because then that can be sent to LLC to create your .s file, which is your object file that's LLVM based. And then you take that unoptimized object file and send it through Clang to do its optimization passes for you. And Clang has some built-in optimization passes that are available to you. And then you have a program that runs. It's crazy. But high level, that's how you create a language. Or that's how you create a language implementation. This is a very good tutorial. I went through this tutorial also. So it's a good tutorial. If you want to understand LLVM and kind of how it works, it's a good tutorial to go through. It's if you printed it out as PDF, it's 50 pages, but it's the most dense and complicated and humbling 50 pages you will ever read. And but it's it's nice. You kind of get tired of I don't know, like you get tired of line of business applications, and so this kind of like understanding this stuff and trying to understand this stuff, yeah, it brings some life back to what used to be humdrum and boring. But yeah, here you go. This is how you do it. So any questions on how to create a language implementation, which is a composition of a language spec, a runtime, and core libs?
No questions in the queue.
Okay. Is this useful? Has this kind of given you an idea of like what all is involved here? It's good. Okay. Glad to see that. All right. So for the final, we got 20 minutes left. Everyone's able to hold on for 20 minutes. Okay, real quick. In 2020, another thing happened. Thumbs down. Whoever's thumb, I bet that was Justin. He's like, I don't have 20 minutes. I'm leaving. I bet you that was Justin. I know you're right here. See, well, I knew it. There he is.
The good news is, if you can't,
there he is.
Yep. This is being recorded. So
cool. Okay, so real quick, WASM. How's WebAssembly play into all this? Well, WebAssembly, as of 2020, I think 2021, end of 2020, became an LLVM backend compiler. So it takes LLVM IR and then converts it into something called WebAssembly that is used to run in a website. Now, I swear, if I have to say another stupid name, I'm gonna have to say another stupid name again. So you have Blazor, and you've got mscripton, and Rust also targets WebAssembly, and the WebAssembly toolkit in Backend Compiler, it's called Wabbit. I kid you not, guys. The WebAssembly binary toolkit, it's called Wabbit. So Blazor is a front-end compiler for C# that creates a Wabbit file. And what does a Wabbit intermediate representation file look like? This makes me so angry. It's called like .wat. Let me find one. I think it's called .wat. Please. There it is. It's a Lisp representation. And this is essentially what Blazor resolves to, is this variant of, it's a subset of the LLVM intermediate representation that's formatted in such a way that it's easy to parse and generate. Because Wabbit does not have an IR builder of sorts, having this kind of structure makes it fairly trivial to generate. So Blazor is doing this thing behind the scenes. Okay. So knowing all this, final thing with WASM. So for those that were giving thumbs up and using the emojis, you were using a web-based application. Well, go here instead. Give you a URL. It's called there it is. There's the URL. So instead of using the Heroku app, go to this URL instead. And what you're going to do, what you're going to get is a, well, you can do the thick client downloads for Windows, Mac, Raspberry Pi, and Linux, but you also have a WASM implementation. And this WASM implementation also works. You should see them coming up, right? So this is we're getting into the final part of the thing, which is Dragon Ruby. And what you're seeing here is a single Dragon Ruby code base exported to Windows, Mac, Linux, for Raspberry Pi, ARM64, and WASM. Our WASM implementation actually goes through mscripten. We don't use Wabbit because we don't have to use that because of the decisions we made in our runtime. And that's what I'm going to spend the last 15 minutes explaining. Okay. Now, there's real power in this. So for those that are on the website, if you press the tilde key, a heads up display comes down. And this is a console window. And this console window can evaluate Ruby code. So this runtime implementation that we created creates this cross-platform binary, but also allows you to evaluate the language itself within the app. So there you have it. Puts hello world, shows up, right? 0.10.map I plus 1 or I plus 2. I take the numbers from 0 to 10, add to them, and do that. I can actually do a HTTP post from here, or HTTP post. You give it a URL, a JSON body, and your content headers, and it will invoke an HTTP post through the runtime itself. Okay, so this is a really powerful construct, and this infrastructure allows for some crazy interesting things. And now I'm going to explain what makes Dragon Ruby. What is the explanation of the runtime? Okay. So any questions on WASM and Wabbit and that stuff? Give Eric a question so he has to say that word.
I will not say it. Simply won't.
Eric, what season is it?
I'm sorry, I didn't hear you at all.
Wabbit season.
There you go.
Duck season, Wabbit season. So, yeah, when you look at a language, a new language that comes out, hopefully you have a better understanding of like the internals and what to potentially probe for to see if it's worth investing in. Okay, so Dragon Ruby. It's the final bit and how we got here. So the question is, why would I ever do this? And I mean, there's a very important quote. And I just have to say that quote. You don't do these things because they're easy. You do these things because you thought it was going to be easy. And that's kind of where we ended up. So we have the concept of Ruby motion, which had a basic head start on the Clang takeover because it actually originated from Apple. Okay. Now Ruby motion is a implementation of the Ruby spec at that point it was 1.9. There's an implementation of the Ruby spec using the Objective-C runtime. Using the Objective-C runtime and Apple's foundation libraries. Okay. Language spec, runtime. So in this case, this Objective-C runtime can do threading. There's no global interpreter lock. It can do, it's ahead of time compiled, but it's ref count. There's no GC. It's Objective-C based, which has the auto release pool and ref count based. And it uses the core foundation libraries. So if I want to do an HTTP post, I'm not using libcurl, I'm using NSURL session. Or if I'm creating an array, I'm not creating an array object like a standard lib vector. I'm using NSArray. Okay. There's a problem with this. The language spec is we're up to 3.0 now. The runtime is supported in Clang, but there's variants of the runtime. You've got 3 variants of the runtime: GNU step, you've got next step, which is Apple's representation, and then there's one other step that kind of abstracts it from there. And then the Apple Foundation libraries, those core libraries are only for Apple devices. So we want to leverage the full potential of what Clang offers. So how do we fix this? We fixed it. It took a long time, and we're there, but we are there. And here's how we fixed it. Okay. So there is still an Objective-C runtime specifically for native interop. Okay. There's a mini Ruby that we extracted that can compile a subset of Ruby code directly to LLVM IR. Okay. This piece handles our communication with our host platform, which is iOS. Okay. There's a similar runtime thing for Android, which uses the NDK. The NDK is written in C++. So the Objective-C runtime conventions and return types do not map to this. So we had to create runtime conventions for C++ to target the Android NDK. Finally, we have our C runtime. And our C runtime has compatibility with Objective-C and C++. This is our bridging layer. Okay. Our C runtime uses effectively does not use the LLVM IR directly, and the branching stuff that this mini Ruby created. It effectively does the translation of your opcode to your intermediate representation. And this is close to the mRuby runtime, which is an embedded Ruby runtime. So using mRuby, we upgraded our language spec from 1.9.2 to a 2.0 plus compliance spec. We use the mRuby parser, which is Bison. So we don't have to worry about parsing the Bison stuff anymore. We have our mini Ruby that we still do compilation for the intermediate representation, which will expand. But this gives us a polyfill where if it's compatible mRuby code, there's a good chance that we'll be able to invoke it. It might not be the fastest thing, but depending on whether the native classes that we created are supported at the mini Ruby level versus the opcode level, but it will work. This polyfill is our stabilization layer. It's our compatibility layer. After that, you've got all these runtimes that we had to create. We have to create a foreign function interoperability interface for Objective-C, Android, Nintendo Switch, which is proprietary, PlayStation, Xbox, and anything else you can think of. Each one of these chipset architectures are different, and we cannot ship these runtime foreign interfaces with a standard license because of NDAs. So our runtime has to be multi-layered. You've got your mruby at the top. We've got a variant of a mini Ruby, which we use internally and eventually will expose out, and then your mruby code gen. From there, we go to our core lib. What is our core lib? What core lib will allow us to target all these platforms? And the answer, the core lib, is libSDL. libSDL stands for Simple Direct Media Layer. And it's been around for about 20 years now. And it is a normalization of OS-specific APIs into one uniform API endpoint. Thread management, IO management, rendering, input and output management, file access, it's all handled. libSDL is effectively sponsored by every organization you can possibly think of that's out there. Steam is built using libSDL. That means Valve sponsors libSDL. The mini consoles that existed, like the retro consoles that you can buy, like the mini SNES, NES, the mini PlayStation, all of those are powered by SDL. So Nintendo, Sony, Valve, Unity uses a libSDL, like for its input. I think if there's a game engine out there that's worth the salt, it probably uses libSDL to some extent. And this consolidation layer allows us to have a core library that is unified across all these platforms. The caveat is that we can't support everything. File access is locked down for a console, so you don't have all access to DIRStat. So you might be able to do a file read and file write, but you can't do everything. These are the limitations, and these are the concessions that we had to make for a core lib, selection. But SDL provided us this stabilization layer that's battle hardened, and we use that as our dependency. So whatever was being used inside of the Ruby libraries that existed for file access, for rendering to the screen if there was anything, for HTTP access, for thread synchronization, we gutted all that and used libSDL instead. Okay, that was one of the big decisions we made for a core lib. So we use our mruby as our polyfill. We have a runtime layer that either does the fast IR generation or does the mruby interpretation and code gen. That all uses a core lib. And then there's platform-specific core libs that are added to this based on whether you have access to it or not. That's all based on libSDL. And then our final thing is our runtime model. Dragon Ruby has an event loop. We took the good ideas from Node.js and added this concept of an event loop. 2 minutes, almost there. Difference is that we don't have any concept of async or await variants. We don't use this. Your event loop, your thread synchronization is handled by us. You're given an async object, and we expose the event loop to you. So with Node.js, the event loop is invisible. You don't have direct access to it. With us, you get an entry point called tick, and this will run at a rate of 60 hertz. This will always invoke. So your event loop effectively is like React's request animation frame, except it's for your entire application. Lula is except it's for your entire application. And by and by exposing this event loop to you, you can create an HTTP request that does your GET, which returns an HTTP object. And then the next reentrant of the event loop, you can look to see if that request is complete and then process the request. So instead of using async and await, and the fact that we expose this top level event loop, it allows you to orchestrate your async APIs as a pipeline of sorts. Okay. So you have an in-memory message bus. You say you process this request. Okay, then invoke this next request and process that and continue going. So that's our async model. We also have a HTTP built in. That was a core load decision, and an embedded web server. So Dragon Ruby, the explicit application itself, if you have it running locally, that's the final piece to this. This is up and running, but I can actually go to the web server that's available here. And this web server exposes developer endpoints where I can go to a code file and find the background color and change it to black. And the caveat, and remember, this is aside from WASM, because WASM can't have an HTTP server. This is available. This is available on all deployed devices, which means that's the final piece to it. Where are my videos? Your channel. Which means that you can do the same thing on an iOS device. So here, I've created a good question how miniRuby fits in. This starts an endpoint. I get the IP address for my Wi-Fi right here. I bring up Chrome, pointing to the IP address, which is being served by my iOS device. And then I can change the code, add properties to it, save the file. Press update, and it updates the file. This is not hot loading in the sense that, or pushing code changes to the server. This is hosting an embedded web server on a device and then evaluating that code on the device itself. Okay. Let me answer this final question. So the question was trying to understand where miniRuby fits in. mRuby doing the initial parse seems to be doing the bytecode gen as well, but you split mRuby and actually have a bytecode through miniRuby for your mRuby API. So this miniRuby implementation is used internally by us until we can get it to the point where we're covering more of the Ruby programming language. So parsing Ruby is really complicated. We can't parse all of it. So, but we can parse a subset of that. And that's what we end up doing. So if we can create a function, we have an option of creating this function inside of C, straight C, and letting it run through the mRuby virtual machine. Or we can create the function in a dialect of Ruby that emits an intermediate representation that can then be optimized. So our miniRuby doesn't support all the features that the full-blown Ruby programming language supports, but it gives us enough useful things that we can code some of this stuff and have some productivity and optimization benefits by coding it directly in Ruby as opposed to going through any trying to do it within the C virtual machine. So our miniRuby creates .ll files that are then mixed into the rest of the code. And slowly that will expand to cover the entire language. Okay. So that is the landscape of languages as they exist today. Is your Akmoji public code available? Akmoji public. I can. The files are the itch code is available. My server side is not, but I can make it available once I tweak it and remove some of the hard coding values and whatnot. But yeah, tell me exactly what you need, and then I can put it out there. Who's crying? Oh, because it's not publicly available. Yeah. This thing worked well. I'm surprised. I was like, hey, let's try to build this thing. It actually worked. It's crazy. Questions, comments? Was this helpful? Did this kind of give you like an idea of what this landscape looks like and how terrifying it is? And try to learn it. I think there's some interesting things that can come out of it. Try the Kaleidoscope tutorial, and it'll just give you a better understanding of what happens behind the scenes and all that. Is it okay if I compare Mini Ruby to the Burst compiler? Yes, but we're trying to retain compatibility. So instead of giving you all the features, we're saying, we're going to give we have a very small subset of features, which is essentially useless, but useful enough for us, and we just need to expand on it. Yep, that's correct. We're basically operating on subset, but we're trying to retain core lib compatibility and object compatibility. We're not going to make you create a native array of something that doesn't implement enumerable. If this is something, if we can define an array inside of an array literal, that's what we'll use. Now see why so many people use LLVM. But so I need to learn C++ to use it. You need to learn C++ to use the IR builder. Yes. There are people that have created foreign function interfaces and bindings for Python, for Ruby, to expose it at another layer, but the core implementation for generating this intermediate representation is written in C++, and that is what you'll have to learn. Yeah. And that's why I know just this much and why Alex does the hard stuff.
Well, thank you, Amir. That was awesome.
Welcome.
Well,
you have my contact information and stuff. So feel free to email me, or if you have any additional questions, at Amir Rajan. There it is. That's my contact information. Reach out to me on Twitter. Website's
you only
the same.
exist on Twitter?
Yeah. AR@amirrajan.net, because I was a .NET dev then, or I still am. And I wanted the .NET dev URL thing. So that is forever part of my email. Feel free to email me or reach out to me on Twitter. I'd be happy to answer any questions y'all have. Yay, claps. Clapping, clap, clap. Sweet.
All right. Thanks, Amir. Hey, thanks for everybody coming. We'll see some of you hopefully in person next month. So we'll send out emails and post information and all that. So see y'all later.
Bye.
Thanks again, Amir.
You're welcome.